Students, we are going to study a new topic today, potential energy of a dipole in an external electric field. Okay, one of the good topic. So we start now. Consider a dipole placed in a uniform electric field. Let me draw the uniform electric field. You know that uniform electric field is parallel lines. Yeah. So this is the uniform electric field. Okay. So many parallel lines. And a dipole is placed. That means a plus q and a minus q is placed at a separation with a separation 2a. And this dipole is making an angle theta with the uniform electric field. Picture is clear, right? Uniform electric field exists. There is a dipole aligned with a degree. That means an angle theta with the direction of the electric field. Now here the dipole experiences no net force but experience a torque tau given by torque is equal to Pe sin theta. Why I wrote directly this one? Because this topic we already studied in chapter number 1. Our topic now, right now, is not that one. Okay. So we know the torque acting on a dipole placed in a uniform electric field, that is tau is equal to Pe sin theta. Now only the actual topic starting. So which will what? This torque will tends to rotate the dipole until it become parallel to the electric field. Okay. So we are going to calculate that work done now. That is the topic. So suppose an external torque, for example, we can mark like a tau external. Okay. External torque is applied in such a manner that it just neutralize, you know that already there is a torque produced because of the existing electric field. Suppose an external torque is applied, it is just to neutralize this torque. Okay, just to neutralize this torque and rotate the dipole from theta 1 to an angle theta 2 without angular acceleration. What I wrote now actually. Assume there is an external torque required. Okay, torque required. That torque will tends to turn the dipole from an angle theta 1 to an angle theta 2 without angular acceleration. Now we know that the equation for work done, always we are writing, right? W is equal to force into displacement. And here we are going to write what is force. The force is equal to T external, work done is equal to torque external and displacement. Okay. So force into displacement, you know that in rotational motion force is actually the torque. So tau external into displacement. Displacement here is theta or d theta. So the amount of work done for turning this one from theta 1 angle to theta 2 angle is, what we are writing is the amount of work done to rotate the dipole in the electric field from the angle theta 1 to the angle theta 2 is. So that we are going to write now the work done. Okay. So work done, W we can write is equal to, what is actually the torque here? That torque we know that P is sin theta, right? From where to where, the limit we want to apply. We already mentioned in the statement from the angle theta 1 to the angle theta 2. So the limit of the integration is integration theta 1 to theta 2, tau external of theta d theta. Okay. Now we can substitute the value of torque now. So tau external is equal to P E sin theta. That we can substitute. You can see here. Yeah? Here you can see. So we can write now, and W is equal to, one more time, okay, W displacement you know already. Yeah? Here the displacement is d theta. We used already. So going to substitute in the above equation, W is equal to integral theta 1 to theta 2, and then the value of T external, that is P E sin theta. Here P and E are constant out of integration, so writing outside P E integral theta 1 to theta 2 sin theta d theta. If you know the identity to write what is integral sin theta d theta, we can substitute and our work over. If you don't know, I am writing here right side, integral sin theta d theta is equal to minus cos theta. Remember, okay, only very few identities you want to memorize. Minus cos theta. So W is equal to PE. Now applying the integration rule, so start square bracket minus cos theta, and lower limit and upper limit mention theta 1 downside, theta 2 upside. So is equal to minus PE, substituting the limit of integration limit now. So long bracket in the middle there is a minus. Replace the theta value with the upper limit now. So cos theta 2, that minus I wrote outside, okay. So minus PE you can see. And then minus cos the lower limit theta 1. So W is equal to minus PE cos theta 2 minus cos theta 1. Okay. This is the general expression for work done suitable for any starting angle to any ending angle. You just want to fill the data here. Some people present this answer in the form of positive form. That means multiply the equation with the minus 1. That is, when you do this one, it will be like other way. Plus PE cos theta 1 minus cos theta 2 also you can write. Both are same. Okay, this work done is stored as the potential energy of the system. This calculated work done is stored as the potential energy of the system. Suppose we go specifically, if we take theta 1 is equal to pi by 2, that is 90 degree perpendicular to the field, where potential energy U is taken to be 0. What I wrote here, suppose the initial position of the dipole is perpendicular, where initial potential energy is equal to 0, then you can write U of theta 2, potential energy at theta 2 is equal to minus PE cos theta 2 minus cos in the place of theta 1 pi by 2, that is 90. You know the value of cos 90, right? 0. So that part you don't need to write now. So U of theta is equal to minus PE cos theta 2. Second term we are not going to write, okay? Or generally we can say minus PE cos theta. Okay, this is the expression we were searching for. Okay, students, how is this one? Simple, right? Simple, beautiful, and small derivation. Without much delay we completed this task. Okay, students, do you have any doubts? You can post it in the comments. I will try to answer your question, okay? And next video we will come with a good topic. Okay, wait for next video. Thank you.